Okay, welcome to our video on exponential functions presented by 3Math Guys. Visit our website at 3mathguys.com and subscribe to our YouTube channel. Okay, so this is continuing our look at function families, and so there's this group of functions we call exponential functions. And so what do we mean by that? In real life, often you're going to see this as some kind of a growth or decay that's happening, compound interest, population problems, spread of disease, depreciation in value. If you've got a word problem that's dealing with any of these topics, that might be a hint that you're probably, not always, but probably looking at something that's got an exponential relationship. So let's look at an example. So here, let's say you had 6 pet rabbits, you decide to breed them, and their population is doubling every year. So let's take that example, and we're going to see if we can represent that relationship between the population of rabbits and time in a table, in a rule, in a graph, and show why that's an exponential relationship. So at year 0, when no time has gone by, that's like our starting point, that's right now, we have 6 pet rabbits. So at 0 we've got 6 rabbits. And after 1 year, that's doubled, right? So we're going to have 12 rabbits. And then 24 when it doubles again, and 48, and then 96, and then 192. So we've got these now. It doesn't really make sense to go negative years. I mean, mathematically, I could say, this should be a 3 and this should be a 3 over 2. But these don't really make sense in our problem. So really the domain that makes sense is from 0 forward. That's going to be our domain that makes sense in the context of this problem. And these would be the range. And so what's happening here? What's the relationship? Well, I've got times 2, right? Over and over, times 2. And when you've got this common factor, that's what's going to make something exponential. There's this amount that's getting multiplied over and over. Or if it's a decay, you might be multiplying by a number that's less than 1. You could think dividing by a number, but usually you want to think in terms of multiplication. Okay, so that wasn't too tough to make our table. How can we describe this table as some kind of an equation or some kind of a rule? Well, I could say my total rabbits is really described as 6 times 2 times 2 times 2 and so on. Right? Well, how do we write that as a rule? Well, I could say I have 6 times 2. How do we show that multiplication is repeating? And that's what exponents are. When you repeatedly multiply, that's an exponent. And so I could say this 2 keeps on repeating. I'm just going to say x number of times. If I kind of use common notation and say my input values are x and my output values are y, then let's take an example. So at 4 years, how many times has that times 2 repeated? 1, 2, 3, 4 times to get to the 4th term. At the 2nd term, it has happened twice to get to the 2nd term. So if I want to know how many times is this times 2 repeated, I just need to know the input value, which is going to be my x values. And so I'm just going to put 6 multiplied by 2 x number of times. And I'll just put y equals here for the total number of rabbits. Okay, and if you're not sure if you wrote the right rule, you're doubting yourself, then try it. It should be a rule that turns these input values into the output values. So for example, if I plug in a 3, then I should have 2 to the 3rd power, 2 times 2 times 2, which is 8. 8 times 6 is 48. And yeah, it works. It turns my 3 into a 48. So that's how you can double check it. Okay. So now we've got what we call an explicit rule that describes this this table and this rabbit problem. We can also represent it as a graph. And so you have to decide how you want to scale your graph. I decided to since I have some big numbers here, I had to think, well, how much room do I have? And so I'm going to count by 15s going up, and I have a little more room. These numbers only go up to 5, so every 2 squares is going to count for 1 as I go this direction. And this is years, and I thought about calling this my y-axis for years, but that's kind of confusing because usually we call this the x and the y-axis. So I'm just going to call this the x-axis and the y-axis, but you can choose however you want to describe it. So this is years, and this is going to be total rabbits going vertically. Well, let's put some of our data points on this graph. So at 0 years, I'm only at 6, which is going to be down here. And at 1 year, I'm going to be at 12, which is going to be somewhere close to here. The graphs don't have to be completely exact. At 2 years, I'm at 24. So let's see, where would I put that? Maybe right about here. At 3 years, I'm at 48. So we'll put that just right about here. At 4 years, I'm at 96. So we'll go up here. Here's 90. Here's 4. It's going to be a little higher than that. And at 5 years, I'm at 192, which is going to be right about here. And there's also, you want to ask yourself, do I fill this in? This is not a continuous function because you're not going to have every possible value between here and here. I'm never going to have 9.25 rabbits or 41.6 rabbits or anything like that. So there are some gaps in this. So I'm not going to draw a straight line. I'm just going to draw kind of a dotted line to kind of give you an idea of the shape that this graph is going to have if I graph it. And that's a shape you're going to see with exponential growth. It starts out kind of flat, and it really starts to skyrocket, and it almost ends up vertical the further you go. And it doesn't quite ever get vertical, but almost. Okay, so now that we've got these 3 ways to represent it, we've got a table, rule, and a graph. It's important to understand how are these things related to each other, because sometimes you might be given this information first. How would I turn that into a table, or how would I turn this into a rule? How are they all connected? And so let's kind of paint that big picture. Well, the first thing is there's this starting value, this initial value, right, at 0, 6. And in my rule, that's going to show up here. On my graph, that's going to be my y-intercept. So I've got this initial value. Right, when my input is 0. And then I've got this growth factor. And that's the doubling that's happening. So this times 2, times 2, times 2, that repetition, that's my growth factor. My growth factor in my rule is going to be the part with the exponent. And then it's a little trickier, but you can also see it in the graph here. Let me kind of zoom in and give you an idea. So where does this times 2 happen in my graph? Well, if I take this height and I come over and I double the height, I'll get to the next spot. And then if I come over and double that height, I'll get to the next spot, come over, and double that height. That's my growth. Come over, double that height, right? So this height doubles to become the next value. This height doubles to become the next value. And so this is where the growth is going to show up on your graph. And just know, if you get any type of a problem that is an exponential relationship, those are the kind of the key things you're looking for. What's the initial value? what's the growth factor. If you're given those, great, it should be an easy problem like this one was. If you're not given those, you might have to go find these values, which is a little trickier, but there's ways to do it. And hopefully that kind of gives you a big picture of what's going on in the exponential function family. All right, thanks for watching.